Hello? Okay, cool. Hi everyone, I'm Mikerah. You might know me as Bad Crypto Bitch on Twitter. I post a lot of memes, not recently, but over the past months I've been posting a lot of memes, just following the zeitgeist in crypto Twitter. Yeah, today I'm gonna be talking about some work that we did as a result of an Aztec grant that we got recently, in terms of making it more practical to actually get to ZKMPCML. So I'm pretty sure most of you who follow Twitter or Discord or just what's going on in the space, you might have seen some combination of these acronyms before. And at first it just sounds ridiculous, right? Who would actually type this? I mean, I did for the slides, but in general, when you see this on Twitter, you're just it's some guy in front of his, oh wait, it's not. Well, you'll see him soon. Yes, some guy like this, tweeting, kind of meditating to make it a reality, but he has no expertise in ZK, MPC, nor ML, and you're kind of just perplexed as to why is there some guy in CT like this. For some context, if you don't know, this is Rick Rubin. He's a famous producer. If you listen to Jay-Z, Kanye West, he's known for being the producer. He has no formal music expertise. He kind of just is there for the vibe check. He knows what people like to listen to. Except he's actually successful, but the people in CT are not really successful. But yeah, it's a good representation of what the state of ZKMPCML feels like. And even when you do see somebody who might seem like they know what they're doing, right? They look all imposing, they have raised tons of money, they have a website, and then when you go on their website, you try to figure out more, what it actually looks like is this, right? There's nothing in the back end. You don't really see anything. There's no code. It's just acronyms everywhere, I guess, for hype. But in this talk, we've actually tried to make it a reality, or at least towards making it more of a reality. So quickly, we'll talk about what we actually worked on, how we did it. So this is the most in-depth part. Some quick results, and then some final conclusions for the future. So what did we actually work on? So as part of a Noir research grant, so Aztec has these RFPs for grants on different topics. We've managed to combine MPC, ZK using Noir, and using a tool called CoNoir that you guys will hear more about later in the day. So we combine these tools together in order to sort of take a stab at ZK and PCML. So specifically what we did is we implemented the building blocks for training and inference of logistic regression. And logistic regression is a foundational model for other ML models that people care about. It has sigmoids, stuff like this. Specifically, we focus more on the training because that's typically the harder part. And that's the part that people care more about. It's sort of where the alpha is, where companies sort of care most about privacy. The data sets, how you do the training, those are typically the things that large companies care about, so we just focus on that. And then once you get that, inference is rather straightforward. So basically, we focused specifically on how we represent numbers. This is a big issue in ML, keeping precision and the accuracy of your calculations. So we'll go into depth about fixed point numbers. And then we implemented some key algorithms that people heavily rely on in ML, specific stochastic gradient descent, and sigmoid function, specifically the logistic sigmoid function. But then once you have this, you can sort of implement other kinds of sigmoid functions. And so quickly, what's logistic regression? You might have seen this in your high school or university courses. It's a model that lets you classify data based off some given features. And then the sigmoid is sort of what you're computing to actually get the classes, right? So you're giving a set of data, you train it, and then you want to say oh, is this a bear or a cat or something else, based off the given inference sample. And then how do you find the betas here? Well, you basically run this optimization problem, and then you calculate how well your optimization problem has done against like the regular data set, which is the log loss here. So basically that's what we worked on. So like a visualization of this is basically we have an MPC network, these 3 nodes. One of them is like malicious. You want to compute logistic regression. And then you want to compute that like the result of the logistic regression computation was done properly. So that's the proof part. And specifically what Noir allows is public auditability, so you can post your proof on chain and get like a verifier. We didn't do any like on-chain stuff for this project, but it's totally possible with the toolset. So how did we actually go about doing this? By implementing this. It looks simple, but it's a lot of work. So you basically implemented this in MPC and ZK, specifically just in Noir. The nice thing about CoNoir is it lets you reuse your Noir circuits for MPC as well. So basically, the way this algorithm works is you have this update function, these beta t plus 1s, and you just like iterate until you converge on the error between like instances of the betas. So basically, whenever you hear like MPC defined, it's usually like you compute some public function over some private inputs and get like a public output. So the public function is this iterative solution. The public result is the final beta, not the iterative betas. And then the private inputs are X and Y, which are from the training data set. So in ML, we care a lot about like how we represent and manipulate decimal numbers. So there's 2 main options for that. So the first option is floating point, which is very common. And it's represented in this format. You have some precision, you have some bias. And you want to like represent like as accurate as possible the floating points. And then the other option is fixed points, which is a little bit less accurate, but is like more transportable across architectures. And it's simpler to define. So the criteria that we sort of use to determine what direction we should go in is heavily based on like Noir. So we want to be able to compute negative numbers. We want to be able to handle relatively large numbers. And we care a lot about performance within circuits. And that's like the key part here. And so we settled on fixed point numbers. Floating point numbers, the operations over them can be slow. Since we're operating over in Noir, it just made more sense to focus on something that has more determinism. Floating points are like better if you have like an FPU. We don't have that here. And it can yield different results, which is not really worth it. Whereas like fixed points, it's faster to do like a lot of operations with them, consistent results across executions, and you can like control loss due to errors and stuff like this. So that's why we focus on fixed point. So fixed point. So there's a specific strategy that we implemented from Katrina Saxena. It's a relatively old paper, but it's very relevant. It's implemented in quite a few like MPC libraries. And the goal is to encode a decimal number into field of integers mod a prime. So in Noir, field elements are 254 bits. So the strategy is to take the first 127 bits and have that be a positive value. And then if you want to represent negative values, then you can use the last 127 bits. However, in Noir, there's this decompose functionality that can either decompose an element into 128 bits or 126 bits. So we decided to just do the 126 bits based off the slide here. And so we don't use the middle bits. And yeah, as mentioned before, we're operating over field elements and not decimal numbers. So you need a way to map, fixed point numbers into field elements. And this process is known as quantization. It's very common. So you use it mainly to save space. And so basically what we did is we scale all the numbers from like a regular data set into this format. So if you have just an integer, you just multiply by 2 to the 16. If you have a decimal, you multiply by 2 to the 16 and you truncate. And this Saxena paper goes over like how to do deterministic and probabilistic truncation. So in code, this is what it looks like. So now we just have like one element to represent one large number as opposed to two. So oftentimes you might see like a fixed point represented in like two field elements. We reduced it to one, so we save quite a bit of space. And then operations over these elements are rather straightforward. Add and subtraction are pretty straightforward. However, for multiplication, it's not as straightforward because you need to be careful with handling the precision and the error, right? So if you naively multiply two quantized numbers, you end up with a large factor of 2 to the 32, and now you need to divide it to get it back to like the right size. So visually, this is what that looks like for positive numbers. Pretty straightforward. C is from the previous slide. I divide it by 2 to the 16, and now you have this like number that's within the correct size. But then for negative numbers, it's not so easy. You might divide and you might get some garbage. So the way to fix that is by flipping the sign and then flip it back once you've done the calculation. But we're not done quite yet. There's this issue of, do you actually end up with the right size elements after doing this operation, right? So for multiplication, both operands should be maximum 63 bits. For addition, subtraction, at most, they should be 125 bits. But when you do this, go back, yeah, if you do this, you may not end up with something that's of the right size, right? So there's a concrete example here. We have this multiplication. You get 8 times b times 2 to the 32. You've divided it, you've scaled it down, but you may end up overflowing here because this final number may still be larger than 63 bits or 125 bits. So yeah, this was done by like enforcing it directly in the circuit. Unfortunately, it adds more gates, but it's necessary to make sure that we don't get into like these numbers and that all the numbers that we get at the end is accurate. So we've kind of we've gone over how to handle decimals in circuits, but we haven't talked about how to handle the sigmoid function quite yet. And this is pretty important, otherwise you can't do logistic regression. So quickly, what this looks like. So you have this like e to the x factor, you have a division. Ideally, you really don't want to implement this in a circuit, right? So there's ways to approximate this. And specifically, there's a construction from Hong et al. From this paper in 2020 that gives a specific sigmoid function that works well for secure computation. So this is what we ended up implementing in the circuits. It's a piecewise linear function, which looks much nicer than e to the x in a division. And yeah, the results, which I think is what people care most about. So we implemented this on a single machine and simulated the 3 parties on a single machine. We ran an honest majority, semi-honest adversary MPC protocol provided by TCO. And we benchmarked the training, specifically multi-class training, across 2 common data sets, the IRIS dataset and the WINE dataset. And so concretely what this looked like, for Noir by itself, this is just the proving. The numbers are actually quite promising with relatively like small instances. But for CoNoir, as you can tell, the numbers are a bit like larger, but this is to be expected, especially for training. That's the part that takes the most time. So for 10 epochs and 30 training samples, it takes about 30 minutes. And then for 20 epochs, 30 training samples, it takes about like twice that, so about an hour. And then when we do the same thing on the WINE data set for CoNoir, once we got like over 30 training samples, the machine we had kind of like froze and would kill the process. So we just have like that text there. And this is contrasted with just like normal, if you're just using like scikit-learn, there's like no fancy cryptography over the same things, then it runs like really quickly and you can run it on your own machine by yourself. So that sounds kind of like pessimistic, right? On a single machine, using regular ML libraries, it's really fast, but using fancy cryptography takes quite a bit of time. However, as part of our conclusions, we're pretty optimistic about this. Once you sort of start applying like hardware improvements, TCO will be obviously working really hard on CoNoir. You can get like a sizable improvement in these benchmarks. Really, it's only like up from here, or I guess down because we're trying to get the numbers down. But up in terms of it should be faster. So we're like very optimistic about this. So yeah, what's next? We have code. You can play with it. We have a full report with like way more details, the stuff about optimization, the stuff about Noir that I didn't get time to go over. Yeah, and please use it. Yeah, we're trying to get people to like use this for things that they might find interesting. Even if you don't use the ML portions, the stuff around like fixed points and matrices, still very useful. So yeah, if you have like a project that you're aiming to build, come see me after the talk. And if you want to learn more details, you can get the report. I want to thank everyone at the Hashcloak team. So I'm the one who gave the talk, but everybody else did the work. So Hernan and Elena are our cryptography engineers. They did all the heavy lifting. Teresa's our project manager to make sure that everything's scheduled on time and get resources done. Savio, who's the product manager of Noir at Aztec, was the one who helped us get this grant by like introducing it to us and answering all of our questions. And in TCO, they were like very helpful throughout this entire process. We kept on asking them a bunch of like random questions and like finding bugs, and they were able to like rectify and fix it in a very timely manner. So, without them, I wouldn't be able to do this project. And yeah, special thanks to them. So yeah, keep up with us. Follow the Hashcloak engineers on Twitter. Very smart people. Highly recommend them. And follow Hashcloak on Twitter. We'll be tweeting more about this in the coming weeks. So yeah, that's it. And then the final slide.
We have some time for questions, so if anybody has a question, Steve can bring the mic over.
Thanks for the talk. I think the memes are amazing. So when you ran it against the scikit-learn and you saw that the scikit-learn on your laptop is like a lot more optimal than doing all this cryptography, did you kind of even before you start working on that, did you do so? The question I have is, when I look at your performance slide, I think the result you're presenting is that the cryptographic way of doing the model training takes more time than scikit-learn, right?
Right.
So, but did you go deeper into what part of the training is taking the most time, and then benchmarking that to the scikit-learn? Because I feel like when I'm new to this cryptographic math, but I kind of feel like there could be certain aspects with the Jacobian or the inversion of the matrix where actually the cryptography may not be optimal. So it probably like just was wondering that if you kind of went a little deeper into like what really takes the time.
We haven't really done that, but before we started the project, we did benchmark training on scikit-learn just to get a sense of how worse can this be? Because we obviously knew that adding the cryptography would make it slower, but we didn't have a sense of how much slower, and now we do. But yeah, that's actually something that's worthwhile. We do have a section in the report about optimizations, but it's not against the questions that you asked.
Oh, yeah, I was wondering, there's different provers that you could use, right? I was wondering, what is like the most performant provers, like ZK provers that is compatible for this Nor MPCML thing?
So we just used what was available in Noir. I know the Noir team is like working on integrating other provers, but we just use what's available, not just in Noir, but in Core Noir specifically. So Core Noir specifically has like their own GROS16 prover, and that's what we used.
Oh, okay.
It's like a distributed like MPC GROS16 prover.
Okay, for sure.
Yeah.
In terms of comparing, this versus like status quo of scikit-learn, right? So you showed the performance differences in terms of speed. Were you able to look into like what the effectiveness difference was, like
the accuracy?
Yeah.
Yeah, it was exactly the same.
Oh, okay. So the quantization stuff you're having to do doesn't actually affect,
Yeah.
at least for a smaller scale
Yeah.
training set. Okay.
Yeah, which is actually pretty optimistic.
Yeah.
So yeah, like I mentioned, there's only like up from here. It can only get faster. Yeah.
Cool.
Questions, come on. Actually, you probably already answered this just now, but do you ever see a full 754 implementation actually adding any value to this, like in the distant future, whenever they're actually finished?
Sorry, can you
A floating point 754 IEEE.
It's possible.
Yeah.
But I think this would be much faster than that.
Okay.
Yeah.
Yeah, it's always going to be performance if it doesn't have any loss of accuracy.
Yeah. Yeah. I mean, there are MPC algorithms for floating point. We just didn't implement them for this project. So it's totally possible. I would just expect them to be slower. Okay. Well, thank you.